So hi class, this is homework assignment number 6 on SLAM, and we are going to practice some more questions about the graph SLAM algorithm, and I will ask you something new about how to make graph SLAM more efficient towards the end of this homework assignment. So there's 3 questions and one new thing, which comes with additional questions in a programming assignment. So let's dive in. In this example, picture a robot that starts at initial position 5. This robot, which lives in 1D, even though I'm drawing this in 2D, sees a landmark with a relative measurement of 2. It then moves to coordinate x1 by taking a step of 7. It now sees a different landmark, L1, with a measurement value of 4. Finally, it moves again with a motion 2. And now it sees the same second landmark, not the original one, at a value of 2. Obviously, when you work it out and solve this, you find that the best coordinates over here are 12 and 14, whereas the landmark coordinates are 7 and 16. But none of the numbers I just told you will be inserted in the question I'm about to ask. Picture the matrix omega and the vector c. I want you to add all these constraints into omega, with the caveat that for the initial constraint, I assume the strength is just 1, so enter it the way you're used to. I also assume the motion update has a sigma of 1, but the measurement update, the sigma for measurements, has a value of 0.5. And remember, we weigh those updates with 1 over sigma, which in the measurement case would therefore be 2. I want you to fill in the values for sigma and for xi for this specific example. I gave you some of the sigma values and some of the xi values, and I want you to fill in the missing values over here. You can check whether you got them correct by verifying that I got those numbers correct, and you can also solve for omega minus 1 times xi, and out should come the red positions shown in the diagram over here. So here's the answer. I filled in all the missing values for you, and let's try to check a few. For example, let's take the elements related to x1. We moved from x0 to x1, which added 1 on the main diagonal. We moved from x1 to x2, which added another 1, so we have 2. But we also had 1 observation in x1. We incremented by 2 because of the measurement strength 0.5. 1 over that is 2, so when we ended the measurement, we ended up with 4. Let's pick this off-diagonal element over here. This was only affected when moving from x1 to x2, and it was a minus 1. This element over here was affected when we sensed L1 from x1. And again, the off-diagonal element is negative, so we added a minus 2 over here. It's quite involved, as you can see. Let's take a number on the right side, the minus 2 over here. This is adding up every contribution to x2. The first one occurred when we moved into x2 from x1. At which point we added 2. By x2, we also measured landmark L1 with a measurement value of 2. We have to multiply it up by 2 to arrive at 4 and subtract it. So we add minus 4, we get the minus 2. If you work out all these examples using the math we explained in class and working in the fact that measurements get a default factor of 2 for every value you add, you'll arrive at exactly this matrix over here. I hope we got a good number of numbers right. That was not an easy task. I now want to ask you the really challenging question over here. And it goes as follows. One of the weaknesses of SLAM is, as we move along and map a world by seeing these landmarks, the matrix omega, which is the big thing here, and of course the vector c, grow linearly with the length of the path. Now this means if you go to your local supermarket and buy a robot, and that robot lives for a long time, say a year or a decade, then this thing here, the path, will be really, really large, even though the environment in which it might operate, the map, might be of a fixed size. And that means a robot programmed by graph SLAM will eventually stop working because it gets slower and slower. Now, we all know computer operating systems that have that property. The older they are, the slower they are. But I'm not talking about how to fix operating systems, just talking about how to fix SLAM. So the crucial idea that I want to tell you about and I want you to implement from scratch in our software is the following. we can actually reduce the map we maintain to one that only contains the most recent position in the path. And all of the stuff over here can be safely erased when we build our map. So you don't know how to do it, but let me tell you. Suppose we have a robot position and we have a matrix omega that only contains the information pertaining to one position. If the position is one-dimensional, it's just one row and one column, whereas we might have many different entries for the map. So suppose this robot moves to a new position. Let's call it xt plus 1. Then we do exactly the following. We grow the matrix and the vector by using the expand function that you're already familiar with, such that we now have space for our new position. The new area we added are these rows over here. It's a single row of numbers if our position is one-dimensional. It's two rows of number if our position is two-dimensional. And it's this column that again is just a single column if our position is one-dimensional. Otherwise it's two column. And we initialize those all by 0. And then we can apply our regular motion update that, as we know, adds 1 or some number like 1 to the main diagonal and -1s off diagonal. And the same on the right side for the vector c. That is a legitimate motion update, but that runs the risk that our path increases. So now we go back to a form like this. We make xt plus 1 survive. Simplified speaking, you might think about doing this by just cutting out the new submatrix that starts over here and the subvector that starts over here. However, if you do this, as you can easily verify, that submatrix doesn't give you the correct answer. And here's where the meat is. We now cut out 3 submatrices or values from the full matrix on the right side. One sits here. That one I will call A. One is over here. It's a single element for a 1D robot, but it's a 2x2 matrix for a robot in 2D coordinates. And one that I call C. And it's obvious to see that this thing over here that we're about to cut out is called A minus 1. These values carry a lot of importance. We can't just erase them, but we can fold them back into the surviving matrix by the following simple operation. We take the surviving matrix to be called omega prime and the surviving vector to equal x prime. And you can get omega prime and x prime by using the function take that is in your matrix library. You have to look into how to make take exactly those elements over here. And then we modify x prime and c prime with the following piece of math. We subtract from omega prime A transpose times B to the minus 1, the inverse, times A. If you implement this correctly, this gives you a matrix of the same size as sigma prime, and that's what you subtract to arrive at our reduced sigma. Similarly, you do the same for C. You subtract A prime minus B to the minus 1 times C. This turns out to be the same as a Gaussian, where we technically do away, or we call it integrate away, the variable x1. And I don't want to go into detail whether that's correct. My book has a multi-page proof of that simple equation. I just want to give you an intuition here, which is these values do carry importance, and to get rid of those, you have to redistribute them into the remaining variables, and that over here happens to be the math. So it's A transpose times B times A that you subtract from the remaining omega prime, and the same for C over here. When you do this, you're now left with a matrix of the same original dimension, because we first added a pose and then we subtracted one. And as you can see, when you do this many times, the final dimension of the matrix is only determined based on the size of the map, plus, well, a single entry, which in the 1D case is one row and one column, in the 2D case is 2 of those, corresponding to the robot position. That means SLAM scales to really large environments because we can do the trick every single time a robot moves. So you ask for a challenging programming assignment. I promise you'll be busy with it for a while. I'm giving you now my piece of code in which I implemented SLAM for you. You're familiar with this. You have all of that. And when I run SLAM with 3 landmarks, 3 time steps, a world size of 100, and a measurement range of 100. I make data at random, as you're familiar with, and I compute the result, and the result in this case contains mu. Then what I might get out looks as follows. There's 3 landmarks. There's a sequence of estimated positions leading up to the actual robot position. They're about correct. And then there's estimates for where the landmarks are. Every time I run it, I get a different answer because my landmarks and my world is different at every time. Now I also implemented, and that's your task now, a function called online slam. And does exactly what I told you to do. It resizes the matrix every time a new motion occurs and then goes back to the original size. And I've printed out here as an example the information matrix omega and the vector c that I obtained, and I also printed out the final result. In the final result, we get exactly the same estimated pose as for the full SLAM algorithm, which is 86.0 and 33.7. So I go down. These are exactly the same number for the estimated pose. That's how you can verify this. The same is true for the estimated landmark. Those coordinates are identical, despite the fact that I reduce the size of omega and c. But when I print omega and c, we'll find that the dimensionality is reduced. It's an 8 by 8 matrix omega, and the number 8 comes because there's 6 coordinates for the landmarks and 1 final robot pose. That is substantially smaller than the matrix I would obtain for the full SLAM case. And the same is true for the information vector of size 8. Here's an example. So what you are asked to do is to fill the entire online SLAM routine. And to do this, every time you get a new pose, you run expand to grow the matrix by inserting something right behind the existing pose. We then run take to take out the submatrix. You also calculate A, B, and for the information vector C. And then as before, your reduced omega is obtained with this equation, and your reduced C is obtained by this equation. If you make no mistake, then you get exactly the same values as we have before, and we can test your routine in arbitrary maps and arbitrary data sets, and it'll just be fine. So good luck. This is a wonderful programming assignment because it gives you the first really scalable SLAM algorithm, and when you implement it, it's actually a major achievement. I can tell you it took the scientific field of SLAM easily 15 years to really discover this form, and ever since, what was really complex and involved lots of Kalman filters, and I can tell you lots of headaches, became amazingly easy. So implement it, and you can call yourself a robotic mapper. So here's my solution to the programming assignment where I asked you to program an online version of online SLAM. Let me run it and compare it to the offline SLAM. When I run it, I get random landmarks and a random initial robot pose. My offline solution gives me this long path over here and estimated landmarks. And the remarkable thing here is that my online version that I coded gives me the same final pose and the same landmarks without retaining this huge matrix for the path before. So how did I do this? Here's my online SLAM routine. In large parts, it looks exactly like my offline SLAM routine. I do it in 2D. I have a measurement and motion step. Here's my measurement update. I have to get all these indices right so you can stare at them for a while, but they're all correct here. There's a +1 and -1 over here. And here's the first non-trivial thing. My matrix so far has 1 robot pose and 1 entry for each landmark, but now I need to add space for the next robot pose. And the way I do this is I make an expansion list using the expand command, and this expansion list retains the original robot pose, which has coordinate 0 and 1. These are 2-dimensional poses, and indices for all the landmarks. So I'm squeezing in 2 no rows and 2 no columns for the next robot pose. That's happening in this code over here. With this squeezed in, I can now do the update. The update is being applied exactly at these 2 new rows and columns that I put in. And here's the math I gave you for factorization applied to this problem, where I go and compute the intermediate matrices A, B, and C that I explained in class. And then I use the take command to kick out the very first row and column, the first 2 of them, to remove the old robot pose, using the exact same logic that I gave you in class. So you can look at this. This actually implements online SLAM.